All right, so first thing we're going to do today is we're going to review completing the square, since some people had some issues with that in the homework last night.
Had a doctor's appointment.
No issues. So completing the square is one more way, of course, to solving quadratic equations. And in fact, it's what we use to derive the quadratic formula. And really, it's good to know about completing the square, but as far as its actual usefulness, there's some cases where it is kind of quick and easy to use it. But generally speaking, we're going to use either factoring or use the quadratic formula to solve an equation. But let's just go over it anyhow. So let's just say I have a basic quadratic equation like x squared plus, let's say 3x minus 11 equals 0. And so completing the square can be used on any quadratic. Just like quadratic formula, it is a universal method that always works. But it's especially useful, of course, when it's not factorable, obviously. Or normally when a quadratic is factorable, we'd like to solve by factoring. But we do need a method in the event that it is unfactorable. In this case, we have x squared plus 3x minus 11 is equal to 0. Not factorable, right? There isn't a factor pair of 11 that has a difference of 3. So we know right away that that is not going to work. So what we're going to have to do then is we're going to use completing the square to solve this. Now, the first step with completing the square is always to take whatever constant that you do have, which in this case is negative 11, and put it over to the other side of the equation. All right, so we're going to go ahead and add that 11 to both sides. Essentially, we're trying to get rid of it from the left side of the equation, put it on the right side. Then, the whole point of, or sort of the whole strategy about completing the square is to take the remaining x squared plus 3x and add a constant to it that is going to make it a perfect square quadratic. Perfect square quadratic is just any quadratic that factors out as just a binomial square. So it's a special type of quadratic, right? So we got to know, what does the third term have to be given the coefficient on the linear term here? What does that third term have to be given this to make this a perfect square trinomial? And so it turns out, because of the pattern that develops with these perfect square trinomials, you can always just take the coefficient on the middle term, divide it by 2 and square it, and that is what the third term would have to be. So we're going to go ahead there. And what's 3 divided by 2 squared?
9/4.
Yeah, that's going to be 4. Sorry, not 4. That is going to be 9/4, yes. So we're going to add 9/4 to both sides. So 11 plus 9/4. We're going to combine that into a single fraction in a second. So that means this is going to factor out to, right? If this is going to factor out into x plus, well, in this case, because it's plus 3x, it's going to be x plus something squared. What does that thing have to be? How do I get the, let me ask you this question. How do I always get the third term?
So what's going to be 3/2.
Yeah, exactly, because 3/2 times 3/2 gives us 9/4. And the 9/4 part is going to come from multiplying the last terms together, right? So it's got to be x plus 3/2. So if you want to figure out what the binomial is going to look like, you always just take this and take the square root of it, which is 3/2. Or you can take the middle, the coefficient on the linear term, and divide it by 2. Either case, that'll give you what the binomial has to be, or the second term of the binomial. Let's go ahead and add the 11 and the 9/4. How many fourths is 11? 44 fourths. So 44 fourths plus 9/4 gives us 53 fourths. So now, how are we going to get rid of that squared on the x plus 3/2, do you think? Let me go ahead and I'm going to put this in the next slide here, just there's no room on the other part there. I have x plus 3/2 squared is equal to 53 fourths. So how do I get rid of that squared right there?
Square root both sides.
Yep, go ahead and take the square root of both sides. What type of square root should I use? It's important that I take the, because how many solutions are there going to be? Yeah, there needs to be 2 solutions because it's a quadratic. So we always have to take the plus minus square root. And that's true anytime we take the square root of both sides of an equation. We have to use the plus minus square root. So we'll end up getting, and the last thing to do is just subtract the 3/2. Negative 3/2. Square root of 53 over 4, can that be reduced? How can I reduce that?
Reduce the 4, right?
Yeah, what's the square root of 4?
2.
So really it's plus or minus square root of 53 over 2, right? And then those have a common denominator. We always want to combine it into a single fraction. Does 53 have any perfect square factor pairs? Or any factor pairs other than 1 and 53? No, so we're good there. So those are the two possible solutions. So that's completing the square. So if we want to go back and review that really quickly, get the constant on the other side, add what you need to make the perfect square trinomial, which is just take the middle term, divide it by 2, and square it. Factor out your quadratic and do a binomial squared. Take the square root of both sides, and then solve for x. Okay. And that'll work every time. Were there any other questions from the homework last night or 2 nights ago at this point? Everything else was good? Okay, cool. All right, so today, inequalities today. And we're going to start out with some really basic inequalities that I'm sure you're familiar with. I'm going to introduce some new notation for solution sets to inequalities, right? And then we're going to talk about something you probably, unless you sort of studied it on your own, are not familiar with, which are quadratic inequalities and other nonlinear inequalities that we can solve using our calculator. So that's probably going to be a mostly new topic for you guys. But let's start with the basics of inequalities first, which you should be very familiar with, and then we'll move on from there. So basic inequalities, right? An inequality is like an equation, except instead of an equal sign, we have either a greater than or a less than, or greater than or equal to, or less than or equal to. So anytime we see one of these symbols, we have an inequality instead of an equality. And oftentimes with inequalities, we like to graph solutions, right, to represent sort of more visually where all the numbers lie that satisfy these. Because in the case of inequalities, usually there's more than one number that is true for the inequality, unlike equations where it's either 1 or 2 or 3, sort of a set number. There's like a countable number of solutions. In the case of inequalities, it's usually a range or a piece of the number line that would be the solution to the inequality. Right, so for instance, a basic inequality like x is greater than or equal to 2, right? If we were to go ahead and graph that, right, that's all the numbers in the number line that are to the right of 2, right? And does that, if it's greater than or equal to 2, would that include 2? Yeah, and so what are we going to do at 2 here?
Fill in the dot.
Yeah, we're going to fill in the dot to indicate that 2 is part of the solution set, and we're going to put an arrow going to the right. Right, so that's how we can sort of visually talk about that. Oftentimes we'll also have what we call combined or compound inequalities, which involve 2 or more inequalities that are linked by a special connecting word, which the word itself has an impact on the interpretation. So for instance, if x is greater than or equal to 2, or x is, let's say, less than 0 here. What if I add that or x is less than 0 part? What else should I add to this graph to indicate what the solution set is here?
Circle at 0.
Yep.
And then an arrow to the left.
Yep, so we have an open circle at 0 to represent the fact that that 0 itself is not part of the solution, right? If x has to be less than 0, it can't be 0, right? We also have, and so we call this particular type, because it's using the word or, what do we call this? There's a couple different words that we associate with the word or. Can you guys remember any of them?
Forgot.
These two regions, the one to the left of 0 and to the right of 2, are not connected. What's the word for not connected? It starts with a D.
Disconnected.
It starts with dis, but not disconnected.
Disjunction.
Disjoint or disjunction, yeah. So we call this a disjunction, right? You got the dis, that was the important part. The junction part's the same no matter what. And we actually have another word for that that's referring to like the fact that this is really a set combination. What's the set theory word that corresponds to disjunction? There's 2 types of set operations that we're familiar with. There is intersection and, what's the other one? Union. This one happens to be a union, because we're saying all the numbers to the right of 2 and all the numbers to the left of 0, take those 2 sets and combine them into a single set, right? That's what a union is. We take all the elements in one set and all the elements in the other set, and we combine them into a single set, right? So you can call this, anytime we use the word or, we're going to call that a disjunction or a union, right, with the word or here. Now, another type of inequality, another type of compound inequality that we have seen. So if I use the word and instead of the word or, on this one right here, what would I get for a solution set? Can a number be to the left of 0 and at the same time be greater than or equal to 2? If I find, is there an intersection between those two sets? Is another way of saying that. Do they intersect at all? Is there any overlapping part?
No.
No. So what would be the solution set?
No real solution.
No solution.
No solution.
There's no number that is both less than 0 and greater than or equal to 2 at the same time. So for the word or, sorry, for the word and, both statements have to be true simultaneously. Any number that's part of that solution set has to meet both of those criteria at the same time, not just one of the two. For the word or, it's less stringent, the definition. Only one of those two things has to be true for the word or. Right? So really understanding what a disjunction is versus a conjunction, a union versus an intersection, what does and versus or mean, is important to really, really understanding inequalities, specifically compound inequalities. These are compound inequalities. Another type, sometimes this can be written like so. So x is, can be read as x is between 1 and 5. Right, that's one way to read this. And we can actually write this as two separate statements. This is just a more convenient way to write it as sort of one full statement right here, which is, how could I break this into two separate statements?
X is greater than 1 and less than or equal to 5.
And it's really important that we use the word and, right? Can't be the word or.
Right.
And let's look at that visually for a second here. So if I were to go ahead and graph this set, here's 0, let's say here's 1, and over here, here's 5. Then it's all the numbers that are greater than 1 and less than or equal to 5. So the 1 we should leave open, right? And the 5 we should fill in, and then we'll go ahead and connect them. So it's all the numbers that are greater than 1 and less than or equal to 5. So this is not a union, right? We're not taking all the numbers in the set x greater than 1 and all the numbers in x less than or equal to 5, and we're combining them into one set, because there are certain numbers that are left out, like all the numbers to the left of 1 and to the right of 5, which would have been in those two sets, are not included. So instead of combining these two sets into a single set, which if we did that, if I used the word or, what would the solution actually be? If I used the word or instead of the word and. If I did a union of those two sets instead of well, I almost let it go there. Instead of this type of operation.
All real numbers?
All real numbers, because they're overlapping, right? And if we took all the numbers in the set x greater than 1 and all the numbers in the set x less than or equal to 5, that's the whole number line right there, right? In this case, though, because we use the word and, we just look for the what of these two sets. That's a word that's more intuitive. The intersection. That's the set operation. It's an intersection, right? And, whoops. So that's an intersection. What's the other word we use for this? It's not a disjunction. It is a conjunction. Conjunction, junction. The overlapping part is called a conjunction or an intersection. Okay. And once again, if we made that or, then the set would be all real numbers. It would just be x is any real number, because if I take all the numbers in the set x greater than 1 and all these numbers in the set x less than or equal to 5, I have every number on the number line. Let's actually go back. So that's it for, there's your basic compound inequalities. Let's look at some, actually before we get into some examples of compound inequalities, I want to start introducing to you a different notation. Instead of using inequality notation to represent these sets, like x is greater than 1 and x is less than or equal to 5, we're going to start using a different notation that is often used more frequently in calculus, called interval notation, to mean the same thing as x is greater than 1 and the same thing as x less than or equal to 5. So let's look at those two. I'm going to use these two compound inequalities we've looked at as examples of showing us how to talk about a set Or now we'll do some more basic ones first. Sorry. In any case, interval notation. Right. So let's say I have x is greater than 2. That's the inequality. What we're going to start calling the inequality notation for that set. But that is a set of numbers that describes, right? All the numbers that are to the right of 2. Now, instead of saying x is greater than 2, we're going to talk about the numbers more explicitly and say, well, 2 itself is not part of the set, but all the numbers from 2 out to what? Infinity. And beyond, yes, are going to be part of that number. And we have to somehow, so we're going to go, the left endpoint, essentially, of this set is 2, and the right endpoint is all the way into infinity. So interval notation uses the endpoints, both of the endpoints of the set, to describe all the numbers in the set. So all the numbers from 2 to infinity are in this set. But we also have to talk about, now, is 2 itself included? No, so if that's the case, we're going to put a parenthesis right there. Now, is infinity an actual number, really, technically? No, so it can't really be included either. So we're going to put, we call this an open interval because the endpoints are not actually part of the set. The endpoints are not part of the sets. Now, what if I had the statement x is less than or equal to -1 on the other hand? Right, let's go ahead and use set notation to describe this particular set. Or sorry, interval notation to describe this set. So it's going to go from, if we're going from left to right in the number line, what's this farthest to the left number that's going to be part of this set? If it goes just to the left of -1. Yeah, negative infinity. So, which is not really technically a number, but we got to go all the way out to all the numbers on the left. So that's how we talk about that. Negative infinity, comma, and then all the way to -1, right? Now, negative infinity, can we ever quite get to infinity or negative infinity? No. So if you have infinity there, that's always going to be what we call a closed end, or sorry, an open endpoint, in that we can never quite get to infinity. So infinity is not really part of that set because it's not really a number. It's just a way of talking about the fact that we're going to go to the left forever. Now, on the other hand, is -1 going to be part of this set? Yeah, so to indicate the fact that -1 is part of the set, we're going to use a bracket. Is that a bracket or a brace? Is that a bracket? Yeah, we're going to use a bracket, yeah. My symbols, I always forget the name of it. We're going to use a bracket to indicate the fact that -1 actually is part of that set. Okay, and so this is sort of a half open set. Like on the left side it's open, on the other side it's closed, or a half closed set, depending on whether you're an optimist or pessimist, I guess. But we will call this a closed endpoint. And it's closed because the number itself, -1, is part of the set. Okay. So we have an open interval, open endpoint, closed endpoint, open endpoint. That's terminology we're going to start using. And so we're going to use this notation now to talk about inequalities. So you can still solve inequalities the same way you've always solved them, which we'll see in a second here. But then when you're done, when you have the solution, I want you to start getting into the habit of writing it in interval notation. Because the thing is, all the answers in the book are going to be in interval notation. So you're going to want to have yours in interval notation to be able to compare them. And I want you to know how to convert from one to the other, just like with any other notation. So let's look at, well, what if we have a compound inequality? There's more than one interval that we have to talk about. And so we can look at similar ones to the ones we just saw. So for instance, with compound inequalities and interval notation, if I have like x is less than, let's say, -3, or x is greater than 1, right? Where we have two separate sets there that are sort of being combined into a single set, right, by the word or. And so let's just figure out what those are going to be by themselves independently, and then we'll talk about how we're going to combine them. So x is less than, and we'll make this greater than or equal to 1. So if x is less than -3, what would that be in interval notation?
Open, parentheses, negative
So open because negative 3 is not part of it. And for x is greater than or equal to 1, Kevin, what do we think?
B,
Whoops, that's actually wrong. Wrong, and I'm leading you. So anyways, go ahead.
B, open infinity
So on the right?
on the left, right?
Well, we go in the order of the number line, right?
Oh.
So positive infinity is all the way to the left, or all the way to the right, sorry. So the 1's going to be to the left of that. So it's going to be 1 comma infinity. And it is open. Infinity should always be an open endpoint. But what about the 1?
Maybe a bracket closed.
Bracket. Now, an OR, what's the type of set operation that is?
Union.
That's a union. And knowing that's important because union is represented by the letter U. So you're just going to write, to combine these two sets with the word OR, you're just going to put a big U in between them. And that means you're taking the union of those two sets. And that's how you're going to write that in set notation. Right? Okay. Now, on the other hand, if I have like x is, let's say, greater than negative 3 and x is less than or equal to 1, so I'm combining a similar but different set with the word and, that's going to end up being, let's write this in the condensed inequality notation first, which is x. How do I write this as a single inequality with the word and? That between notation. Negative 3, yep.
Negative 3 and then less than x. And then x is less than or equal to 1.
Yep. So essentially we're saying x is between negative 3 and 1. So how would I write that in interval notation?
Parenthesis negative 3.
Yep.
And then would you just put 1 with a bracket?
That's all you got to do. Because it's just that one set from negative 3 to 1, right? Including 1, but not including negative 3. So it's the left endpoint is open, the right endpoint is closed. An alternate way you could have gone about that is to write it in set notation or in interval notation first, is to sort of bypass this middle part here, which doesn't really matter how you do it, but you got to write the simplest possible set. So if you had said negative infinity to negative 3, and then what type of operation is this? It's an intersection, and we use the symbol for that as an upside down U, right? And then we go 1 to infinity, right? Oh, but including 1, sorry. Now, we have to look at that and say, is that the simplest possible way to write that? And in the case of intersection, if there is a solution, it's never, we pretty much never end with the intersection symbol in our set, because usually there's a simpler way of saying that, which is to say, well, the intersection between these two sets, sorry, I completely screwed that up. Let me rewrite this. It should be negative, because it doesn't make sense otherwise, right? Negative 3 to positive infinity for x is greater than negative 3. And then it should be, for this one, it should be negative infinity to 1, right? And then the left side needs to be open, and the right side needs to be closed. Okay, so if I'd actually written that correctly, we look at these two sets and say, what's the intersection of negative 3 to infinity and negative infinity to 1? And the intersection just is negative 3 to 1. So you would want to go ahead and write that like that. So we essentially have two different ways of doing this. This is the alternate method, right, which is just as valid as long as you understand the intersection operation. Right. Generally speaking, though, you're going to often, in many cases, you'll end up with a union sign still in your intersection note. In your interval notation for your solution, but you usually are never going to end with an intersection sign. You'll end with a union sign, but not an intersection sign, because if you use an intersection, there's usually a simpler way of writing. Okay. And we did talk about the fact that this notation here always means the word and, never means the word or, so it's always an intersection, not a union. Okay. So that's how we deal with the actual idea of the sets when we get to the solutions, but sometimes we don't have the solutions right away, we don't have the sets right away, we have to solve the inequality first, which can be a little more complicated. But really it's not that bad because we're just going to follow all of our general equation solving skills to, or use our inequalities. So for instance, if I have like 3x minus 1 is less than or equal to 5 and greater than or equal to negative 4. Actually write that so it doesn't look so crappy. All right, so there's a compound inequality that's not solved yet, right? We don't know what x is less than or equal to or greater than or equal to, so we want to go ahead, and I'll make that just less than. We want to go ahead and solve that. We're going to solve that by just using basic operations on both sides of the inequality, right? But what I would do is I would break it up first into two separate statements. But in any case, for solving inequalities, same as solving linear equations, the process of just adding and subtracting and multiplying and dividing both sides of the inequality by the same number, because we have the same properties. It's not the inequality, it's the, well, they're like the properties of equality, but they don't use the word inequality. The properties of order, which are like the properties of equality that say that you can multiply, divide, add, and subtract to both sides of an inequality by the same number, and it won't screw up the inequality. You'll still have the same solution set. Except, what's the big exception with inequalities that you have to be careful about that's different from equations?
So you divide by negative sign.
Yeah, you got to switch to, if you're dividing or multiplying by a negative number, you have to switch the direction of the sign. So the big exception, except when multiplying and dividing by negative numbers. Right? So, why don't you guys go ahead and solve that one and also the next one. I should be able to get enough of it.
Still write it in interval notation?
Yes, and please write your answers in interval notation for both of these examples. And on the homework tonight as well, all of your inequality problems, make sure you write them in interval notation. So go ahead and give these a try. The first one, I think the best way to do it, you can do it by keeping it together, but you're less likely to make a mistake if you break it apart into two separate inequalities first. So that's what I always recommend doing. So write it like this, and 3x minus 1 is less than or equal to 5. And so you'll end up getting that 3x is greater than negative 3, and so x is greater than negative 1. Notice I'm dividing by a positive number, so even though I'm dividing a negative number, that doesn't affect the direction of the sign, right? So I should get x is greater than negative 1. Then over here I'll get 3x is less than or equal to 6, so x is less than or equal to 2. Put the and in between there. So it's greater than negative 1 and less than or equal to 2. And so I'm up in the corner here, I'll write it in interval notation. So negative 1 to 2, open parentheses for negative 1, closed bracket for 2. Okay. And this other one down here, we want to go ahead and subtract the 8x from both sides. So we'll get negative 5x and add the 7 so that we get is greater than or equal to 10. And so we have to go ahead now and divide by negative 5, which means we should change the direction of the inequality. So it's less than negative 2. Okay? Oops, and I want to write that in interval notation, so I'm going to write less than or equal to negative 2, so negative infinity to negative 2, and that's going to be a bracket for closed. Okay? So that's the big thing with these types of inequality problems on the homework tonight, is that I just want you to write the answer in interval notation. All right, it's been a little bit less than 40. Why don't we take a break?